Michael and his Fleet colleagues will now lead a presentation on Fleet's impact and legacy, highlighting key achievements across 6 impact areas: knowledge, sustainability, capacity, STEM education, innovation, and leadership. Thank you for joining us today, and over to you, Michael.
So I'm going to try to tell you about what 200 people did over 7 years in 10 minutes. So as Joanna said, Fleet's mission is to reduce the energy that's used in computing and create a sustainable future for information technology. So I'll try to unpack that a little bit just in a couple of minutes and tell you a little bit more about what that means. Some of you probably don't know too much about what Fleet does, so I'll try to explain what we're trying to do. So the background is that all of the computing that we do, so essentially all of the devices that we use to do wonderful things with information, rely on the basic unit of those computations is a transistor. So a transistor is a solid state switch. It uses a voltage applied to one electrode to either allow a current to pass between 2 other electrodes or to turn that current off, to block that current. So it has an on state and an off state controlled by a voltage. Okay, so it's a little switch. The thing is, we're very good at making these switches. We can make them, we can mass produce them. So what you see here on the left is an image of a silicon wafer, which contains microprocessors, and those microprocessors, there are 800 microprocessors on this 300 millimeter wafer. Each one of those microprocessors contains 1.4 billion transistors. So on that wafer are about 1 trillion transistors just on that one wafer. And those are coming out of the fab, the factory that makes them, quite rapidly, right? So we're very good at making these transistors. We can make lots of them, and then we can do really powerful tasks with information with those transistors. So the technology that is used to make those transistors is called silicon CMOS. It doesn't really matter too much what it's called, but it's been in place for about 50 years, since the late 70s. And the reason that we have used this one technology for all of that time is that at that time, in the late 70s, it was realized that if we made transistors with this technology, they were okay then, but every year we had a plan for how to make them a little bit better. We could make them a little bit smaller, slightly lower voltage, pack more of them onto a chip, and they'd be a little bit more energy efficient, and they would also run faster. And so every year we had this plan to make this transistors a little bit smaller, a little bit cheaper, a little bit faster, and a little bit more energy efficient. And that turned out to be really great. There's this roadmap for improving things year by year, and it worked fantastically well. So on the right, what you see is the growth in computing capacity around the globe. And this chart covers about 2 decades, but really this growth happened over about 4 decades. Computing capacity grew at about 60% per year, which is just astounding, right? Nothing grows at 60% a year for more than a couple of years, right? So 4 decades of growth at 60% per year, which is really amazing. And that technology allowed us to build 10 to the 22 transistors by today. So that's 10,000 trillion transistors. Wikipedia tells me there's 10 to the 18 grains of sand on Earth. So it's many more transistors than there are grains of sand on Earth. It's obviously by far the most of anything that has been built by mankind, humankind. So this is the thing that we are really good at doing. Humans are essentially the transistor making ape. This is what we do. We make transistors and we use them. But this technology that we've used to make all of these transistors, which has been fantastic, is really kind of running out of steam. We're unable to keep making it slightly smaller and slightly faster and slightly more energy efficient every year. And that is having a cost. So the cost is that every year this increase in computing capacity means that we're using more energy to do computing. And so the energy that is used in computation is shown here in the green line. And that is rapidly moving towards the yellow line, which is the world's energy production. Currently, computing uses about 10% of the world's electricity, but you can easily extrapolate to computing to use all of the world's energy, electricity, and not within a couple of decades. And so one of two things will happen. Well, if we stay on the current course, computing will be strongly limited by energy production, and that will be a very finite resource. The amount of computing we can do will be limited by the amount of energy that we can produce. So we would like to be able to do more computing. We'd like to be able to do better, greater things with computers. So computers make every other industry more energy efficient. So it's a good thing that we have this resource. We would like to use computers to better model climate change and understand what's happening. We'd like to use computers to understand how proteins fold to make a virus and how that virus structure determines, how the virus infects. We'd like to use computers to design better drugs that have fewer side effects, right? So there are things that we want to use very complex computing capacity for, and so we want that resource. And it's a good thing. So this is where Fleet comes in. Fleet is looking at how to make a better transistor that switches at lower voltage and uses lower energy. And it's that basic unit of computing. So it's really going back to the drawing board, the very fundamentals, and trying to redesign that transistor. So I'm going to try to tell you a little bit about how that's gone over the last 7 years. I'm going to tell you 3 little vignettes, little stories about things that Fleet has done related to that mission, to give you a bit of a flavor of that. So first, I'm going to talk about this concept of a topological transistor. This is something that Fleet proposed in 2016. There are new materials called topological insulators that are insulating in their bulk. They don't conduct in the interior of the material, but they conduct on their boundaries. And so if they're two-dimensional, if they're very thin, they conduct along their edges. And they can conduct perfectly along those edges without resistance or without any dissipation that would turn electricity into heat. We proposed that topology could be switched on and off with an electric field. So we could apply a voltage, and that would switch the material from this topological insulator with these fantastic conducting edges to a regular insulator, which is insulating off. It doesn't carry current. And so that would be the basis of a transistor. So a radical idea. It had never been done, and it was something that we proposed as a major part of the center. And by the end of 2018, we had actually demonstrated that in a particular material, sodium-3 bismuth, we could accomplish this switching. We could switch that material from a topological insulator to a conventional insulator, on and off. And so that was fantastic. We went on to then show that these topological materials, due to strong spin-orbit coupling, actually had an advantage over CMOS, that they could switch at lower voltages. And then we've gone on to show other designs for devices which we think really could be very competitive with CMOS. So now this concept is on the semiconductor roadmap, the international roadmap for devices and systems, the IRDS, as a promising beyond CMOS device technology. And there's a spin-off company that has that's been formed to license this technology that was developed in Fleet and develop it further. So we also had a vision of using a very different kind of particle to do computing. So this is a thing called an exciton polariton. It's a bit complicated, but it's the quantum mechanical entanglement of a particle of light, a photon, and matter, or electrons. And in particular, it's an electron that has been excited in a semiconductor and leaves behind a hole. And that electron binds to that hole, which is positively charged. The electron's negatively charged. It forms an exciton. And then that exciton can then have this very strong interaction with the photon and form this entangled half light, half matter particle. That gives it some very unusual properties. This fact that it's made up of light and made up of matter. And in one property in particular is that you can form superfluids out of these exciton polaritons, and they can flow without resistance. So that's another, that's, again, this flow without resistance is something that we thought is very promising for making a device that uses low energy. So the challenge here was that this resistanceless flow had actually been observed, but at very, very low temperatures, essentially 4 Kelvin, very near absolute zero. And so what we wanted to do within Fleet is bring that up to room temperature. We thought any useful device, anything that's going to be in your phone or on your desktop, is going to be at room temperature. And so we need this to work at room temperature. How do we do that? So we decided to look at using atomically thin semiconductors, new materials of just a few atoms thick, where we could make these excitons. They'd be strongly bound at room temperature, and they would work at room temperature. And so, so we did that. It was a big engineering challenge. It was interdisciplinary work. It involved people that knew the materials, people that knew how to make these photonic cavities, people that knew how to study them with lasers, ultra-fast lasers. And so it's it requires this big center-sized effort to bring all those people together to do it. And we did it. We were able to make these excitons, these strongly interacting particles, at room temperature in 2D semiconductors and observe their behavior. We did not get them to condense into a superfluid, which would have been really fantastic. That's like a room temperature superconductor. But as you know, room temperature superconductors are pretty difficult. But we did observe some really cool behavior in these excitons in 2D semiconductors at room temperature. So this is a picture. It's a bit of a complicated picture, but essentially it's a snapshot of what these excitons are doing, not in real space, but in momentum space. And so left and right are basically means that they're either heading to the left or heading to the right. And these collections of excitons, these bright spots, you can see are either all on the left or they're all on the right. They're not down in the bottom of this curve. And that's a behavior that you would just never, ever, ever see in electrons in a semiconductor. That basically they all are collectively moving to the left, all together in a big herd. And that's something that just wouldn't happen in a semiconductor, but it's happening with these exciton polaritons, and it's happening at room temperature, and they're maintaining this very coherent behavior, and they're doing it over really large distances. It's tens of microns, but that's large on this kind of device scale. And so really interesting behavior that's going on in these new kinds of particles, and it's happening at room temperature. Lastly, I want to tell you about a discovery that's actually kind of serendipitous. You may have gotten the point that a lot of the science that Fleet is doing is underpinned by two-dimensional materials that are just a few atoms thick. So we were very interested in how we could make more of these two-dimensional materials. They're a bit difficult to make. And Fleet had this fantastic center where we brought together chemical engineers and people with expertise in electronics and material scientists. And as it turned out, some of our scientists were very interested in the properties of liquid metals, and particularly the chemistry that happened on their surface, and discovered that you can use the surface of a liquid metal as this really fantastic reaction vessel to make two-dimensional materials on the surface. And it's a self-limiting process. They grow, and then that's it. You get one layer and it stops. And so turns out that that's just fantastically efficient to make lots and lots of two-dimensional materials. We immediately used this to make a kind of gallium oxide glass coating that helped us protect our 2D semiconductors and allowed that work that you saw in the previous slide. And so we applied that to the work that Fleet was doing. But it turns out it's useful to doing things like carbon capture, catalysis. You can make filters out of these 2D materials. So there's lots of other applications. And that all came out of the fact that, well, we needed 2D materials, and we also happen to have this interest in liquid metals. And so, and it's really cool stuff. There's also a spin-off company that's pursuing this research. So, so that's kind of the thing that happens when you put together a bunch of people that are really good at what they do, and you task them with some kind of new problem. Okay. Lastly, I don't want to drown you in KPIs at all, but I want to point out a little bit, just maybe one little story, one sort of quantitative story about the outputs of the center. We started off, I mean, you put 200 researchers together and you give them some funding, and they're going to produce scientific outputs. That's like sort of a given. We wanted outputs that were impactful, right? And so we picked a KPI that we thought was ambitious. We want 20% of our papers to be high impact, right? So things that are really important, those important papers. One out of 5 papers, that would be really fantastic, right? So as it turned out, we were able to have over half of our papers, over half of the papers that Fleet produced during its run, were high impact papers. They were in high impact venues. And so, and that was just really fantastic. It's something that was unexpected. We didn't dream that we could have half of the papers be that, have that level of impact. But this is what happens when you bring people together and you task them with something that's a very important problem. You give them the resources, the time scale to work on that problem, to work together, and they can produce things that really matter. And that is the thing that I think centers can do, right? And this shows it that yes, of course we produce papers, but half of them, more than half of them, were in high impact venues, and I think that's really fantastic. Okay, I probably took more time than I was supposed to. I'm going to, what you're going to hear is several stories about Fleet, not just the knowledge creation that I've told you about, but some of the other aspects of what Fleet has done over the years. Next, I'm going to hand to Kiralee Rule, who's going to tell us about capacity building and what we've done there.